Okay, we're back to talk about a few more things that you studied last year, and actually a couple of things that you didn't look at last year. We're going to start off with voltmeters and ammeters, and this is how we get our measurements for what is happening in a circuit. A voltmeter measures voltage difference between two different points in a circuit, whereas an ammeter measures current. And in class, we have tools that can help us to measure both of these for the same through the same machine. It's called a multimeter, but it is important to know whether you're using your multimeter as a voltmeter or as an ammeter, because if you hook it up wrong, there's a very good chance that you could break whatever you're trying to do. A voltmeter that measures potential difference, it has to be wired into a circuit a certain way, and that is because the voltmeters themselves have extremely high resistances. Now what this means is that if you plug a voltmeter into a circuit the wrong way, if you hook it right into the main branch of the circuit, it'll cause the resistance of the circuit to go through the roof. And you don't want that, okay? You don't want the voltmeter to draw current, because then it's drawing current away from what you really want the current to go through, and it'll screw up your readings. So the voltmeters don't draw current, so they are placed around the circuit component that you're trying to find the voltage difference around. And a picture of that would look like this. Here's your, let's say, resistor. Okay? Your voltmeter won't just be attached to the end of the resistor. It will actually the leads on the voltmeter will go around the resistor. They'll kind of surround it. V, like this. So this is a voltmeter in a circuit. An ammeter is a little bit different. An ammeter, or ammeters, have very low resistances. So they don't affect the current of the circuit, and they are placed, I guess I'll say, directly into the circuit. In other words, if this is your resistor and you want to know the current going through it, an ammeter has a very low resistance so that it doesn't change the current of the circuit that you're looking at, because if you had a very high resistance for an ammeter, it would affect the amount of current that's flowing through the circuit. They have very low resistance, so they don't change the current any appreciable amount. They can get wired directly into the circuit itself. It actually would break the ammeter if you hooked it around the object like the voltmeter here, because then you would get a surge of electricity, a surge of current through the ammeter, and that would actually usually, in our multimeters at least, trip a switch and it would break things. We don't want that, okay? So, and I'll come back to this after we do types of circuits, and I'll talk exactly about what this is called, these particular arrangements, but then we will, and we'll talk about what the actual term for how we're hooking these up is. But we have to get to types of circuits first. Before we get there, let's talk very quickly about cells and batteries. You already know what the pictures for these look like from the front of the sheet. For any cell or battery, it has a rating on it, and you're used to seeing these: 9 volts, 1.5 volts, 12 volts. The rating tells the potential difference between the poles of the battery. The poles just being one end to the other end. Positive to the negative end. Poles of battery. Like 6 volts, 9 volts, 1.5 volts, etc. Okay? Now, that's the basics. Everyone knows that that's how a battery works, but there's going to be there's two things that I'd like to talk about right now that are kind of slightly more advanced. If a battery, because you might encounter this a couple times on homework, if a battery is connected I guess what I would call backwards, it acts like a resistor and causes voltage drop, not gain. This is also how we charge batteries. Let me draw you a picture. Let's say that we have a stretch of circuit like this, where we have two cells, but the orientation of the cells is different. Okay? So we have two cells. Let's say that this is a 6-volt cell, this is a 9-volt cell. And you can see that the orientations are different because the alignment of the big line and the small line are flipped for each of these. If we were to set a voltmeter around each of these, they would tell us, well, this one would say 6 volts, and then this voltmeter would tell us 9 volts. However, if we were to put a voltmeter around the entire thing, it would not tell us 15 volts. That's because the orientations are different. Assuming that this, there's some resistors down here that I just didn't draw. Assuming that the 9-volt battery here is really what's driving what's going on here, the current will go all through the circuit. It'll get back to the 6-volt battery, but because it's hooked up opposite, it will actually lose voltage right here as opposed to gaining voltage. For the 9-volt battery, if current is flowing this way, it'll gain, there will be a voltage gain from one side to the next. There will be a voltage loss from here to here if the current is going this way. So if there's a 9-volt gain here and a 6-volt loss here, this voltmeter will say that there is a 3-volt gain in total on this section. Okay, that you're going to see that very, very rarely, but I did want to introduce that to you just to make sure that you understand that. The last thing I want to talk about with cells and batteries that we didn't cover last year is that they are not perfectly ideal. They may have some internal resistance. What this means is there is some resistance, just like wires have resistance, and obviously resistors and lamps have resistance. There is actually possibly some internal resistance incorporated in the battery. It's not resistanceless. May have internal resistance, and this is incorporated into the resistance of the entire circuit. Okay? What this does is it brings us to a term called terminal voltage. And that means the voltage difference between the poles of the battery if we're accounting for any internal resistance. Terminal voltage is given by this equation. Vt equals kind of the curly E thing, EMF, minus IR. Vt is the terminal voltage of the battery. The E is the voltage gain of the battery before internal resistance is accounted for. And then this IR term is the voltage drop due to internal resistance. So what internal resistance does is it effectively lowers the voltage that actually comes out of the battery. There would be more voltage if there weren't an internal resistance, but in a non-ideal setting, you do have to deal with that. Okay, you do have to deal with some resistance in a battery, but that only occurs when we're only going to deal with that when it specifically tells us to. Okay, now we're going to move on to types of circuits. We're going to deal with 3 different types of circuits this year. Last year you talked about 2. The first one we're going to talk about is the most basic. It's a series circuit. And in a series circuit, there is one branch or one path for current to follow. All circuit components, everything in the circuit, is linked so that the current only has one path to follow. So a picture of a series circuit might look something like this. Here's your battery. Here's a resistor. Here's a lamp. And then it connects back. There's only one path for all of that, for all the charges in there to follow. It has to go through each resistor, through the resistor and through the lamp. Okay? Let's see here. So some notes about a series circuit. First is that the current is the same throughout the circuit. Because there's only one path, so the current can't deviate. The voltage drop across each resistor depends on the size of the resistor, in that bigger R leads to a bigger voltage drop. And lastly, the total resistance, or equivalent resistance you might hear, called Req, is given as follows. Req equals R1 plus R2 plus R3 plus ... as many resistances as you have. And I will make one last little note that for this, when Req is found, it is like multiple resistors are combined into one. And what we mean by that is, even though these are separate, if we look at the equation for Req, the equivalent resistance, it's just simply adding the resistors up. It's almost like you take these two objects with a resistance and you kind of just push them together to get an equivalent resistance. That's like saying, okay, what if these were really the same resistor? All right, there's series circuits. Those are pretty easy. You shouldn't have any real trouble with series circuits. Let's move on to the other type we talked about last year, and that would be parallel circuits. All right, we're doing good on time. The other type with parallel, the main difference is that in a parallel circuit, there are multiple branches or paths for the current to follow. Current has choice of multiple paths. So it splits in some places. Here's an example parallel circuit. Here's our battery, just the same. And our battery has, let's say that there's a resistor right there. And so right now this is just a series circuit with one resistor in it. I'm going to make another branch, and on that branch is the light bulb. Okay? So you can see that the current There are two different options or two different loops that the current can make. The current can go, the charges can go from the battery through the resistor and then back to the battery, or they can go from the battery through the lamp and back. They cannot go through both. There's a choice here. It either goes through the resistor or through the lamp. The current won't go back up the way, like it can't go down the resistor and then back this way. That's not how current flows. It wouldn't go that way because it's almost like swimming upstream. You can't do that with circuits. The electric potential difference won't let you. The rules for parallel circuits are also different. Okay, so whereas a series circuit, the current was the same throughout the circuit. In a parallel circuit, the current decreases from the total in the branches. Let's see here, what else? The current in each branch is determined by the size of the branch's resistance. In other words, if there is a bigger resistance, that leads to a smaller current. The voltage drop in each branch is equal. And that is interesting. So the voltage drop in each branch is equal, and it must be equal to the voltage gain for the battery. And the reason for this is that otherwise, when the branches rejoin, the charges as they flow would have two different voltages or energies, which is impossible. So in other words, if this battery had a voltage gain of 6 volts and this resistor had a voltage drop of 2 and 4, like you would in a series circuit, then the charges would get down here, and depending on where they came from, they would have different amounts of energy. And that's not how this works. That they would have different energy levels that they're carrying. And that wouldn't make sense. You wouldn't be able to tell which branch they came out of. Or you would be able to tell which branch they came out of, but that's not what we observe. The voltage drops in each branch are the same because each location in the circuit has a specific energy level assigned with it. And if they didn't have the same drop, then you wouldn't be able to get to these energy levels, and that would be bad. We do have a couple of equations that go with parallel circuits, and they've kind of been stated already. The total current is equal to the current in branch 1 plus the current in branch 2, and so on and so forth. And the equivalent resistance is given by this equation. 1 over Req equals 1 over R1 plus 1 over R2 plus 1 over R3 plus ... Okay? So parallel circuits, a little bit more complicated, but you dealt with them fine last year. The most complex type of circuit that we're going to deal with this year is actually, I'm going to call it a complex circuit. So complex. And a complex circuit, or a compound circuit, whatever you want to call it, is a mix of series and parallel. We did not deal with these last year, but this is going to be the focus once we get up into the higher level circuits. A complex circuit might look something like this. Here's our battery. Here's a resistor. Right now this is just a series circuit, but I'm going to add in another branch here. So this is a mix of series and parallel because all of the current must go through this element of the circuit, but then there's a branch off where this current could either go through this resistor or this resistor. So we have these two being in parallel, but each of them is in series with this. So how do we analyze complex circuits? Typically, you're going to find the equivalent resistance first. You're going to do this by isolating the smallest section of the circuit that is just series or parallel. So for this circuit, it would be this section right here. This is just a parallel part. You would find Req of that section. And then move on to the next biggest section, and so on and so forth until you find the equivalent resistance of the entire circuit. Okay? So for this example, as I kind of alluded to, you find the Req of the resistors in parallel. Then once you find that Req, add that, because these resistors are in series with this circuit, so you just then add that to the third resistor. And I know that's not a great way of explaining it, but we will get some practice with this so that it becomes a little bit easier. And once you see these, they're actually kind of fun to try and figure out how the resistance works. All right, so that is a little bit about voltmeters, ammeters, cells and batteries, and the types of circuits. In the next video, we'll get into stuff that you haven't done yet. Okay, so that's stuff that maybe we've mentioned, but you haven't really studied in detail. I'll be back for that later. Bye.